Alright, so again, what I'm going to show you, this is a technique, a graphical technique, how to find an image using what's called ray tracing. So what I'm going to do is I'm going to start writing the rules down, and we're just going to kind of do it together. So as I write the rule, we'll kind of draw them out together. And the first few times it gets a little tricky, but then it becomes a piece of cake. And one of the things to think about, you always want to go back to the visual that I gave you of the theory of the mirror, how it looks. Probably the hardest part about this unit is mixing up all the different mirrors and different lenses that we're going to deal with. So go back to that first visual, what a concave mirror does. Okay, it looks like this, and that'll help guide you. Alright, rule number 1 is this. We're going to draw a parallel line from the object to the mirror. We're going to draw a parallel line from the object to the mirror. One aspect of the mirror I forgot to tell you to do, and I'll do that right now. You can just put it right here. Is on your mirror, can you just draw like a vertical line perpendicular to the ground, the base? Okay, like this. And the reason for this is all of you are kind of drawing different size mirrors, and depending on how the mirror is drawn, you're going to increase or decrease your accuracy. So we're going to draw all our lines to this vertical line in the back. And you're going to reflect it off the back. Just know in the back of your mind, reality is that the light actually hits the mirror and reflects. But for the purposes of this, we're just going to go all the way back to this vertical line. So let me show you what I mean. So the first one is you're going to line up your ruler. And actually, you'll probably have an easier time doing this because you have lined paper. But you basically want it, when I say parallel, I mean you want it to be parallel to that base that you drew. So we're going to draw this, and we're going to go all the way back to that vertical line in the back. That's my first beam. I'll call this beam number 1. Okay, now this is going to hit the mirror, right? It's going to reflect off the mirror, and actually you should already know how it's going to reflect. What direction is this going to reflect up here? Down, and specifically how down? Through the focal point, right? Look back at this picture. All parallel beams end up going through the focal point. So what you're going to do is you're going to reflect the line through the focal point. Reflect the line through the focal point. So you take your ruler, line it up where it hit the back part of that mirror. You line it through the focal point, and then you just send it on through. So this is beam number 1 here. Okay? Easy enough? Beam number 2. Basically, beam number 2 is the opposite of what we just did. So this time you're going to draw a line from the object through the focal point. So you can take your ruler, line up F, this, And again, go all the way back to that vertical line back there. Okay, now I can already tell I'm off a little bit, but it's okay. If you do it in pencil, you can always erase and, you know, fix it. So anyway, this is going to reflect. Well, you guys can probably tell me, how is this going to reflect? We're doing the opposite of what we did before. So we're going to reflect the line parallel. Take your ruler, line it up, make it parallel. Ooh, wow. Okay, looks like that. That's beam number 2. The red one is beam number 2. Okay, that's it. And this one, the first one you can see is kind of obvious based on the theory I gave you. This one, though, if you think about it, what would happen if we went in reverse? If I went in reverse, this red beam, notice this would just simply be parallel through the focal. So this is, I'm just choosing the beam that happens to go through the top of the arrow. So these two are identical type beams, conceptually speaking. All right, third one, there are 3. For all of these that we're going to do, there's 3. Third beam is this. You're going to draw a line through the center of curvature from the object through the center of curvature. Okay, so you take your thing, you line it up with the center here. You're going to go ahead and draw it. Like that. So purple is beam 3. Okay, now here's the thing. This, the way it is, it doesn't quite, it looks pretty decent. This hits right on the normal. Any line that goes through the center of curvature is going to hit right on the normal, which means what's going to happen to the reflected beam? It just goes straight back. Yeah, it doesn't change its angle at all, it just goes straight back. So it comes in like this, and it goes back the same way. So you don't have to continue drawing that. You can just know, okay, I've drawn it once. It's just coming back along the same line. If you want to extend it out here, you could. But it's just going to maintain the same path for both. Okay, so that's beam number 3. So draw it straight back. Alright, so if you did this properly, you should have a nice 3-way intersection. All 3 of your lines should have come together at a point right here. Okay, now if you have a little triangle like this, it's alright. Okay, just kind of center it. Draw your dot in the center of that. If you have a big triangle, then go back and check your lines. Some of them are probably not accurate. So remember, the tip of this represented the tip of the arrow, the tip of the object. So what I'm going to do is just fill this in. So this means my object now looks like this. That's my, sorry, not my object, my image. This would be my image right here. This little upside down arrow. Okay? So conceptually, what do you notice? What are some characteristics of this image? Upside down, yeah. We use the word inverted, but upside down is okay. Is it larger or smaller than the object? Smaller. Okay, and this is what we refer to as a real image. A real image. So what a real image is, real images, in a nutshell, they actually exist. In other words, unlike a virtual image, which required a human to actually be there to see it, a real image is actually there. So a human doesn't need to be there, the light's still there. So a couple things to think about. Well, essentially what I just said, light will intersect to form the image. In other words, these three beams came together, intersected at a point, formed an image right here. And then the basic rule of thumb is it will show up on a screen. So if I were to put a little piece of paper here, which you're going to do this when you do a lab, you're going to put a little piece of paper here and you're going to see the image show up on the screen. It'll show up right there. Okay? In fact, what you're looking at right now is a real image. So what you're looking at with this projection is a real image. So light's coming through here, going through here, light's coming onto the screen. It's projecting onto the screen. So this right here would be considered a real image. Okay, what I would like you to do next is to go ahead and make a few measurements. So I want you to measure the image distance of your image. So just take your ruler, measure the distance from here to the mirror. I'm getting about 5.8. Hopefully you're in that ballpark. So I would say, all right, my DI is 5.8. Hopefully you're in that ballpark, 5.7, 5.9, 5.6, 5.5, something like that. Okay, again, you're measuring the distance from here to the mirror. Okay? That's my DI. The next thing I would like you to measure is the HI. Now, I don't think I've used that word before, but what do you think HI stands for? Image height. So how tall the image is. Okay, so take your ruler. Measure the height of the image. Getting about 1.1 maybe. Let me go with 1.1. Hopefully you're in that ballpark. 1.0, 0.9, 1.2, 1.3-ish, something like that. So we're going to find out in about a minute who's right, or which one of us drew these the best. Okay? All right, any questions on where we're at right now? Okay, so just like pretty much everything in physics, some guy comes along, finds a mathematical relationship with all this stuff. Let's see if I'll leave this. There we go. Okay, and this is called the mirror equation. So here's what the mirror equation looks like. We're going to go 1 over f equals 1 over di plus 1 over do. There's two big equations in this unit. This is the first one. Okay, 1 over f equals 1 over di plus 1 over do. Okay, so when I made my measurement, I got 5.8. Let's see if I drew this perfect, what I should have got. So we'll call this like our experimental image distance. Let's see what our theoretical should have been. So what we're going to do is we're going to plug in the actual givens. So I gave you 4 centimeters for your focal. Let's find out what di we should have got. If you don't have your calculators out, go ahead and pull them out now. My do was 14. Now if all your units are in centimeters, you can go ahead and keep them in centimeters. If you want to convert them, that's fine too. I'm just going to write my answer in terms of centimeters. So make sure you plug this in the first time. People have trouble the first couple times. Actually, you might not. We've seen this equation before, right? Where did we see it? Parallel circuits, yeah. Parallel resistors, equivalent circuits. So again, what you do is subtract 1 over 14. You get some number. It's going to be some weird decimal-y number, right? Like 0.1 something, I'm guessing, or 0.2. What's the answer if you just do this? 1/4 minus 1/14? 175. 1 over di, but that's not the answer, so be careful, don't stop there. What do you have to do now? Reciprocate it. And one of the nice things about this unit is you kind of already know what you should be getting. So we know we should be getting around 5.8. What are we getting? 5 point what? 6? 6-0? Okay. So I was off a little bit. Did anyone actually measure 5.6 on theirs? Oh, good. So a few of you have got some skills. So that's going to be our di here, 5.6. That's the true di. So if you drew it perfect, that's what you should have gotten. Okay, that's the mirror equation. The next thing is what's called the magnification equation. Magnification equation actually has 3 parts to it. So M is what stands for magnification. And conceptually, what do you think is meant by magnification? Yeah, how much bigger it is, right? So if you think of that, you could probably even derive the equation yourself. I mean, if our object was 2 centimeters and our image turned out to be 8 centimeters, what would be the magnification of that? If we started with 2 and we ended with 8, what's the magnification? 4, okay? Because 8 is 4 times larger than 2, right? 4 times larger. So magnification is how many times larger an image is. And so we write that mathematically as HI over HO. So if HO was 2 and HI was 8, then that would be 4 times larger, right? So that's the meaning of that. And you use this with microscopes. Remember you had those little lenses, maybe it was 10 times. Usually they had like a 10 times and a 40 times, and then you combine it to get 400 times. But anyway, this is what you'd use. Now it turns out there's another equation, proportion that's also true, and that's negative di over do. So this is the second big equation. These are the 2 big equations for this unit. Pretty much all we'll use for this unit. Alright, so let's go ahead and calculate what our HI should have been. If we drew this perfect, I got an HI of 1.1. If you drew this perfect, what you should have got. So we're going to use the second half of this. So we're going to go HI over HO equals negative di over do. And let's use what the givens were. So my given for HO was 2. my DI. Now let's use the true value, okay, what we should have gotten. So we're going to write negative 5.6 divided by, my DO original was 14. So hopefully it's something like 1.1. Huh? 7? 0.8. Okay, that sounds about right. 0.80. I just gotta say, this is probably the worst drawing I've ever done. And it's on video. Great. So this is my HO right here. Okay, that's going to be 0.80. Now, did anyone in the class actually do 5.6 and 0.8? One person? Wow, that's good. Amazing. So these are hard to. These will be hard to do, especially the first few times. If you have graph paper, you will improve your accuracy if you do it on graph paper. Okay. Last thing I am going to have you to calculate. Actually, this wasn't the number you got, was it? What's the actual number you got? Negative. Yeah, you should have gotten a negative. So let's just talk about the meaning of the negative. Actually, you could probably tell me, what is the meaning of the negative? Okay, so that means it's inverted. Okay, be careful. Negative does not mean smaller. Negative means inverted. Okay, it's smaller because it is smaller. We started at 2, we ended at 0.8, so that means it's smaller. But the negative means inverted, not smaller. If it was negative 20, it'd be a larger image, but still inverted. Okay, last thing we're going to calculate is the magnification. Whoa. M equals, well, at this point you can use either thing. Okay, HI, HO, DI, DO. I'm just going to use HI over HO because that's the true concept of magnification. So we're going to go negative 0.8 divided by 2. So I can do this math. Negative 0.4. And remember, this was centimeters, this was centimeters. What's the units for magnification? There are no units, okay? Centimeters cancels. So it's just telling you how much larger or how much smaller it is. So in this case, let's just look at a couple things. First of all, what does the negative mean? Inverted again. And what is this 0.4? What's the meaning of that number? So it means, conceptually, it means it's smaller, right? It's a smaller image. And the amount of, how much smaller it is, well, it's 40% smaller. 0.4 times is small. Okay? What number would this be if it was the exact same size? 1. What number would it be if it's larger? Okay, larger than 1. Yeah, so anything larger than 1 is larger. Anything at 1 is the same. Anything at a decimal, right, less than 1, 0 to 1 would be smaller. And then negative means inverted, positive means upright. Okay, any questions?